Alright. So I want to talk today about one way in which the only melody approach we talked about a little bit last time to the ungrid conjecture is different to the length conjecture. And so one thing that comes up is the following. So let's suppose look at the projection map. And we're going to think about an arbitration move variety, but for simplicity we'll focus on the case of the J function. From the upper half plane to the nth power, to the nth power of the modular curve is a projection map. We have two algebraic varieties, in this case it's just semi-algebraic, W, and W is in pi inverse V. And so we want to conclude from this sort of picture that there's something special between W and V, one of these sort of Hackett translates or sort of a concept of a Hackett translate, something like that. And so one sort of intermediate step we'll define this guy I. With a set of elements gamma inside the group of biholomorphisms of h to the n. So that if I look at gamma acting on W, I get another algebraic variety inside h to the n. And I want to insist that it's also inside V. I want to do it in a definable manner, so I intersect with this f to the n. Okay? That sort of becomes analogous to something we defined in the case of length conjecture. Okay, so we can certainly do this, and then I is certainly definable in the structure Rnx, again, because everything inside is definable. And it's very important for this, by the way, that W be definable inside h to the n, and therefore that would be algebraic. Right? That's a key for us. And so what we want is that if I look at the counting function for I, for say rational points or integer points, actually we're going to care about, let's put a z here. You want this to grow at least as fast as some power of t. Okay? So in other words, the picture is that sort of we have this fundamental domain inside h to the n, and also every element of s to z to the n gives us a translate of it, so we have this sort of division into blocks, that we use for length conjecture. And W sort of runs through those blocks, and we want to know that W hits many of those blocks. So, in other words, i.e., number of gamma in SO2Z to the n with height bounded about by t, such that W intersects the gammath translate of f to the n. We want this to grow at least as fast as e to the delta. Okay, where you can define like the height of A, so A1, B1, C1, D1, A and B and C and D. It doesn't actually matter how you do it. You can just define the max as all the A's and all the B's and all the C's and all the D's. Okay, because we only care about something so loose, any other way you define it is sort of going to be very comfortable. Okay, this is one of the key statements we sort of need in this case to prove the analog of the accident conjecture, which we haven't actually fully stated yet. But one key difference is that if you recall, last time we did this in the line conjecture case, the exponential function, we had this for free. We sort of knew that we went from infinitely many fundamental domains. Then we had this sort of graph argument to argue you can only grow linearly fast as long as you're connected, sort of any connected set. Whereas in this case, that's sort of, well, it's plainly not true. Somehow you can, first of all, it's not true because, let me just draw a thing here. And I'll just draw sort of the one-dimensional decomposition. Sort of looks like this. You have other guys here, and it sort of continues on. So there's two reasons it's not true. One reason is that the fundamental domain now, there's some non-compactness going on that wasn't going on before for the exponential function. Right? I mean, there was still a non-compact fundamental domain, but the relevant part, the real part, gave us like a nice little division to squares, which were compact. So the relevant pieces were still good. So here you can have a path which just sort of goes through two fundamental domains. And that's not going to give you infinity. But sort of even if you don't, even if this like were compact, if you take a Shimura curve, or let's just say you take some sort of slanted path down from here to the boundary, it's still going to go through logarithmically many different fundamental domains if you work it out. Okay? So, I don't know, not free in this case. You need sort of a little fun. Okay, so there's sort of a few different ways. This was a problem for a while. There are a few different approaches to it. And so I don't want to start historically. I want to start with what ended up working in general. And then I'll say a little bit about the other approaches. Yeah, so one way to resolve this sort of issue is by looking at volume estimate, being sort of a nice input to this whole story. So let me start with the following. Sort of key lemma. And I'll start in we're sort of in the hyperbolic setting over here, but I'll just start in the Archimedean setting so we can get a feel for it. Suppose you have some analytic curve in D squared, so where D is sort of the, D is the unit disk in the complex plane. And C is analytic. And just so we don't deal with sort of annoying issues of compactness or things getting crazy, let's ask for it to be analytic in the neighborhood of D squared. End of dimension 1. You can see just some holomorphic curve in two variables. And let's suppose that the origin 0 is in C, so 0, 0. And the statement is that the volume of C can't be super small. So in fact, the volume of C is minimized when C ends up being a single coordinate, in which case it's pi. So volume of C is at least pi times. So actually for us to be enough to just say that at least pi. But naturally what comes up is at least pi times the multiplicity at 0. of C. Okay? So you can define this in general, but sort of one nice way to define it here is you pull back the two coordinate functions to Z, and you look at the exponent that sort of gives you the holomorphic coordinate on C. Okay, so before we sort of get into the proof of this, and this is due to Federer in like early 20th century. So one note is that this very much relies on the fact that C is analytic. So very false if C is a real surface. And one way to see that is you can sort of look at the point. Here's like 0, 1. This is three-dimensional, but whatever. It's like the unit d squared. Here's the origin. And C, if it's a real surface, you can just take it to be sort of a really thin tube, starting at 0 and going out of the disk. And the thinner the tube is, the smaller the area is going to be of C. You can sort of pinch it down to a line and pinch it a little bit to make it arbitrarily small. And somehow the holomorphicity forces it to be like more opening up or something like that. I don't know. Is this clear? The real surface is like here? Okay. So yeah, the idea is to show that holomorphic curves can sort of go to infinity without acquiring quite a bit of volume. This is a sort of fairly simple idea which ends up going a long way. Okay, so the proof is rather simple, at least if you're comfortable with sufficiently delicate versions of Stokes Theorem. So I wanted just to give a sketch of it, to give you an idea what goes into it. So first I want to, a little bit of notation. So recall that we have sort of the differential operator D, which could be written as del plus del bar. And you can define a differential operator, d bar, as far as you can, by del minus del bar, and we'll normalize it, dividing by 2 pi I. Okay? Okay. And so we can define a 2 form, a 1-1 form, in fact, W vol in the following way. It's essentially dx1 wedge dy bar plus dx2 wedge dy2, sure? And so, like, the fact that sort of makes all this work or gets started is that the volume of C, if C is analytic, you can write as the integral of this 2 form. Okay, that's sort of magical. I mean, there's no 2 form which, for any real surface, you can integrate and get its volume. In particular, because if you flip it to surface, you get negative the answer. So like, you want this guy to be positive. And there's no sort of way that will orient all real surfaces at once inside C squared. But all holomorphic guys can be oriented in the following way. So they have a natural orientation. Multiplication by I gives you an orientation. Yeah, so I mean, this is a local statement. It's not hard to check. You can also check it because sort of both these guys are invariant under the unitary group, sort of locally. And if C is just a this in one coordinate, then this is obvious. Regardless of how you want to see it, this is a true fact. Okay, so let me first run through the calculation of the case when this 2 is a 1, in which case it's sort of obvious. Calculation becomes easier to think about. Bless you. So we start with the following thing. We start with the fact that if we look at 1, it becomes the integral over the disk of dd bar log z squared. Okay, now this is a little bit confusing because dd bar log z squared is actually 0 as a function, right? Log z squared is log z plus log z bar, and d bar kills log z, and d kills log z bar. If you work it out, but as a current, this is all the sense in which I'm talking about, you get a logarithmic singularity at 0, so that gives you a 1. Okay, so this is all as occurrence. See, I don't want to say too much about this. Another way to think about this is you can sort of use Stokes Theorem to keep shrinking this down into smaller and smaller circles, and then you can do the calculation locally. But regardless, logarithmic singularities give you some contribution as current, and so this becomes true. And so at this point, we apply actual Stokes Theorem, and get that this is integral to the following thing. Right? So another way you think this is current is because Stokes Theorem won't be true unless you do that. This is actually equal to 1 if you compute it. Okay? So this is along the boundary of D. This is along like norm z equals 1. So then I'll explain this in a second. But because we're on norm z equals 1 with a function of norm z, we can change this to, sorry, I don't get this either. No, we can change this to just the of z squared, d bar of z squared. So I'll explain this transition in a second. And now we do Stokes Theorem again. It's the integral of d bar of just norm g squared. And if you d bar norm g squared, you just get 1. Sort of properly normalized. And so this just gives you integral of dz wedge d bar z, and then because normalization, we get a 1 over pi. This is the volume of d divided by pi. Okay, to recover that the volume of d is equal to pi, bottom of the circle, radius 1, which is great. Let me explain how this step works. Then I'll say a little more about that. So for star, if you look at d bar of some function of another function, or d of it, what you get is f prime of g, f is holomorphic, multiplied by d bar g. Okay, this is if f is holomorphic. And so for us, d bar of log z squared is equal to 1 over z squared times d bar z squared. And since we're on the boundary where z squared is equal to 1, those two are just equal. Okay? So this is kind of random, but sort of the idea is we use Stokes Theorem to sort of take this boundary integral and we extend it down in two different ways, one of which captures the entire volume, and one of which focuses the potential sort of at one point. This is the one point, and this is the entire volume. We have these two functions. The same in the boundary, but do very different things inside. All right, so that's the one case. So now for the actual case of n equals 2, we want sort of similar functions, similar looking functions. So we said big F of z1, z2 this kind of function, take the max of two coordinates. And so one nice thing is that f being at most 1 actually defines z squared. Exactly. Both of these guys being at most 1. That's one property. And a second property that's important for us is that f is what's called plurisubharmonic, which means if we restrict f, let phi of z be f restricted to some linear subspace, say, then phi of point z naught is at most the integral of phi of z naught yes, 2 pi I. If we integrate phi in a small circle, it's bigger than the value inside. So these were equal would be harmonic in one variable. This means subharmonic. And then plurisubharmonic means it's true if you restrict to any one-dimensional disk. Okay? And the reason we care about, so first of all, it's sort of obviously subharmonic because these two guys are, so you check, and max of two BSH functions are BSH. Also you check. And so this sort of implies, or is equivalent to, dg bar f is positive. So if having like no singularities, it just means that this is like a positive volume form. In general, it means it's a positive current. But we'll leave all these worlds of current behind after I'm done with this exam. It's in your thing. I just want to give an indication of what the idea is. Okay. And the other thing, before we sort of use that log v squared as a logarithmic singularity at 0, so now f, if we're restricted to c, isn't quite so nice. But if we look at, so if we take z to be a local coordinate on c, as we get closer, such that like z equals 0 maps to the origin, then if we look at the pullback of f, then it's sort of Lie long number, which is this. Sorry, I don't need this. If we look at sort of which power of z of log, which power of z f looks like, so which constant of log z squared log f looks like, you sort of exactly get, or in general, at least get the multiplicity at 0. So I sort of potential with a point on C calculate the multiplicity. Okay, and likewise, del bar log f with the same reasoning is a pluri-subharmonic function. So just to write out the argument and see how it goes. So we start with the multiplicity at 0 of C. But it's not quite enough. We also want to add function equals in this case. So if we integrate del bar log f on C the disk, so dd bar of log of these guys actually vanishes, everything behaving nicely. Then at 0 you get this kind of contribution, and it's also singular along some locus, and so you get some one-dimensional contribution, which works out to be this. So ignore this if you sort of are annoyed by it. The idea is just like before, we integrate del bar of some function, integrate the multiplicity. This is dd bar. Now we apply Stokes Theorem. This gives us d bar of log f. And just like before, so this is the boundary of the squared. Just like before, we can switch that log f to an f. And then we can fill it in. Of d bar f. And now if you look at d bar f, so this is sort of less than or equal to, well, dd bar of these two is at most the volume at every smooth point, because the volume is actually dd bar of this guy plus dd bar of this guy, both of which are positive. So we get at most the volume of C. But we also end up having a one-dimensional sort of singularity again along Z1 equals Z2. And that contributes along this same locus the d bar f contribution. And it's supposed to be normalized somehow, which I didn't keep track of. So maybe this is probably divided by pi. That sounds right. Sorry, the constants are probably a little bit off. Okay, so here is where this magical fact came in. You can integrate a two-form along holomorphic curve and get something out of the volume. And get a volume. Okay, so now, if you work it out, this guy, these two are both positive, because their forms are both PSH, we can only get positive contributions. And dd bar log f is what? Well, this guy is exactly d bar f divided by f again, and f is less than 1, so this guy is bigger than this guy. So we get the volume of C over pi, because it leaves the multiplicity plus something positive, which we have no idea how to control, but we don't really care. Okay. Okay. Any questions about that proof? I mean, it's very straightforward if you're sort of comfortable with currents, which I am not personally. So if you're not comfortable with currents, you can sort of make the same proof work, only now you got to decompose into chambers, sort of where you actually draw this sort of thing on C, as sort of smooth curves, and you integrate inside each guy, and you apply Stokes Theorem on your boundary, you end up getting the same thing. Well, so regardless, this is true. And so now if you just scale the result, you get that the volume of C intersect the disk of radius r, or any number r. And in fact, don't look for 2 here. You can do the same thing in any dimension. This is at least sort of what you expect. It's at least pi r squared times the multiplicity at 0. Another cool thing about this sort of proof is that it does give you sharp results. Because you can obviously achieve this if C is just a single coordinate. You get this radius r with this area. And it also characterizes if you follow the proof carefully, it characterizes those n disks as the only cases where you get sharp results. Okay, so you could do the same thing with more complicated functions, but the exact same idea of proof in the hyperbolic case. And it's all due to Wang Tong in 2002, who did, the case of h to the n. He also handled the case of every other Hermitian symmetric space. And so if you take a point z naught, h to the n, let B of z naught r be the hyperbolic disk of radius r. Set to the z naught. Okay. And you let C be an analytic thing. Again, same thing. Inside here, analytic in the neighborhood. Just so we have reasonable intersections with the boundary and such stuff. Then the theorem is again that the volume of C inside here is at least the multiplicity at z naught of C multiplied by the volume, and you write an n here to indicate the n dimension, just by the volume of a disk coordinate in dimension 1. So again, it's optimizing the single coordinate hyperplane. And for those who aren't familiar, the volume of a hyperbolic disk of radius r, wrote it down here, is 4 pi sim squared of r over 2, which basically behaves like e to the r, up to a constant in some correction terms. But you get something which is essentially exponential in the base. Okay? So the moral is that holomorphic curves pick up a lot of volume as they grow in hyperbolic disks. Okay, so now the idea is sort of pretty simple. The idea is you look at your W, and it's one-dimensional, take a one-dimensional thing inside it, call it C. Look at it inside a disk of radius r. On the one hand, its volume is pretty big. On the other hand, the idea is that on the one hand, the volume is big, and on the other hand, its volume inside any fundamental domain, which is fixed, is going to be small, and therefore has to go through many of them. Okay, so that's the basic idea. So let's do.
Sorry, what's C?
So for us, in our context, well, we have in our context we have W inside pi inverse V, and we want to show that W goes through many. So I'm not sure if you have the question, but okay. So we want to show that W goes through many fundamental domains. And so if W is one-dimensional, then you can just take W equals C. In general, you just take C inside W.
Oh, I mean Z.
Oh, what's Z?
Yeah.
It's
So
probably Z naught. I just forgot to put the 0.
that's dimension 1, right?
This disk here?
Yeah.
This is dimension 1, yeah. So C inside this disk also has dimension 1. Sorry. Dimension C equals 1. And you look at its volume inside this ball. Yeah. Sorry, is everything fixed, or maybe I didn't fix something else? And it's at least this quantity, yeah. And so yeah, we'll apply it to an algebraic guy inside W of dimension 1. Okay. So we need two sort of simple lemmas for this. One is that suppose we have some fundamental domain intersect a ball of radius r around I. Or, any fixed point would just take the point which is I in every single coordinate in the upper half plane to the end. With gamma in SO2Z to the end. Then the height of gamma is bounded above by, well, so some power of r is enough, but 4r is certainly sufficient. Okay, this will be important because we're going to, in the end, show we hit many fundamental domains, but we also want to hit that the gammas we pick up aren't too big. So otherwise, it's not empty. Yes. That's right. Okay, this is fairly elementary. First of all, you can reduce immediately to the case where n equals 1 by splitting up the various coordinates. So then if you write gamma of this, you call that gamma times z is az plus b over cc plus d. And now if z is inside, is within hyperbolic distance r to I, then it's not hard to show that, first of all, the imaginary part of z, right, z is x plus iy, the imaginary part of z is bounded above and below by exponentials in r, because all you can do is sort of go straight up. This is how far you get. And therefore the real part is bounded above by r times e to the r, because you can travel fastest at height e to the r, and that's how far you get, which we'll just record as e to the 2r. We don't really care, but being careful. And so we know that 1/2 is smaller than the imaginary part of anything inside the fundamental domain. So most the imaginary part of gamma z, which if you work out is y over cc plus d squared. And so therefore, you get this kind of inequality, C and D, just expanding this out explicitly. And this leads to C is at most 2 over y. That's bounded above by e to the r. And then you plug it back in, and you get D is bounded above by e to 2r. Just because x, y, and z aren't so big, so D can't be so big either. This is sort of very elementary. It can be done with much more generality, but in the S to Z case, it's very explicit. And so then you can find, by the Chinese remainder theorem, A naught and B naught, which are integers of size at most C times D, which is e to the 3r, such that A naught, B naught, C, D is in S to Z. So all you got to do is solve A naught D minus E naught C is 1. At which point you can write ABCD as some translation of A naught, B naught, C naught, and D naught. And then it's not too hard from here, so by computing, you get that M can be bounded by e to the r, and therefore A and B are bounded above by e to the 4r. So that's what we want to do. Okay. So did I be wrong?
No. What are this? What's C naught and D naught are?
Oh, there's no C naught and D naught, sorry. Just C naught and B naught, yes. Sorry, thanks. Thanks for the grimace. Yes. Okay, yeah, good. So, okay, this for the one hand, so this tells us that all the guys who intersect inside this ball of radius R, all the fundamental domains come into play. The coefficients that show up in S to Z, which will then give us something for the counting function of I, are bounded above by e to the 4r. So the important thing is it's something polynomial in e to the r. And then the final other ingredient that we need is that the volume isn't actually too big in any one of these fundamental domains. So again, so if C in h to the n is an algebraic curve, then this lemma states that the volume of C intersect gamma f to the n is uniformly bounded above for gamma. Well, we only care about gamma as to Z, but S to Z is not definable or nice in general. So in fact, we're going to prove this for all of S to R to the n. Or S to C is actually also fine. So yeah, and you sort of move around different fundamental domains. Any single one of them gives you only a fixed finite amount of volume, most. So the proof, so this volume, as we discussed, is the integral of, in this case, is the sum of dzi, d bar zi, divided by the imaginary part squared. So if we want the Euclidean volume, we remove the y squared, but we want the hyperbolic volume, we put it back in. And now we can treat each of these separately. And so what we get is something which is at most the volume of the fundamental domain times n times the max degree of a projection from C intersect gamma f to the n to a coordinate. Right? Because if we integrate dzi or drzi over some curve, which is at most n to 1 over the base, we can just project down and we get this guy n times. So note that, yeah. So, in this case, it's sort of obvious because C is algebraic, so it's got some degree of every coordinate. You can just take that degree. In general, it doesn't break up algebraically quite so nicely. So here's an argument which is fully general. What you do is you say the degree of the ith projection, one of these guys, is finite for every gamma, and is definable over gamma in SL2R to the n. So you have sort of a family, these guys, which is definable over SL2R to the n. They project this H guy. And so we showed earlier, when discussing homonymity, that if you take any definable family and the projections are bounded, and they're uniformly bounded. So therefore, this degree is uniformly bounded. Okay, so now to conclude the statement, all we do is we take the volume of C intersect the ball around I of radius R, and on the one hand, it's at least as big as e to the R, and on the other hand, it's a sum over gamma in SL2Z to the n such that C intersect gamma f to the n is not empty of the volume of C intersect. Sorry, C intersect, this is not empty of the volume of this intersect this guy, just breaking it out into different fundamental domains. And then we know that each of these is bounded above. So this is bounded above by the number of such gamma. And all of them height at most e to the r, e to the 4r. Times this universal constant we got up here, and therefore the number of these gammas, these are all integers, such that C intersects that translit is at least e to the r, which if you replace this with t, gives you t to the 1/4. And so that gives you polynomially many integer elements in I, and allows you to start the relevant machine. Questions? Okay. Next time we'll talk about what happens with monodromy in this context and sort of say more about the X rhythm and analog.